E si vede tutto bene?
Sì. I think we can start. Hi everyone, it's a great pleasure to have Francesco Tombesi as speaker of our today colloquium. Francesco is now associate professor of astrophysics at Vergata University of Roma. He got his PhD here at University of Bologna in 2010, working with Palumbo and Massimo Cappi. And then he moved to United States, working at NASA, Goddard Space Flight Center, and at the University of Maryland. Francesco's main research interests are the physics of accretion and ejection of supermassive black hole, but also the feedback impact of AGN winds in the host galaxies. Francesco is well known to be a very high expert in X-ray spectroscopy and ultra-fast outflows. He received a lot of prizes, for example, the NASA medal for exceptional achievement in science, and also the Aspen Institute Italy award. He's part of several X-ray missions like XRISM and XP and several other, and also multi-messenger observatories, like for example CTA and also LISA. Today he will. We have some problem. Okay. Today he will talk us about the power, the impact of a black hole wind.
Okay, so thanks for the invitation and for all of you for being here. I see the warmth of people. There are a lot of people here now. And so I would like today to talk a bit about black hole winds. I will focus more on extragalactic objects. I worked also on galactic black holes, but today I would like to focus more on extragalactic, so supermassive black holes, and the possible connection between the accretion onto supermassive black holes and galaxy evolution. And at the end, I'll show you some results that may show the presence of a little crowd around supermassive black holes. So this one is the, let's say, one of the standard pictures that we have about active galactic nuclei. I remember this from more than 20 years ago when I was studying here in Bologna. So basically we have an object, potentially a supermassive black hole at the center of virtually every galaxy. So nowadays we know that at least, so every galaxy hosts at least one supermassive black hole. And galaxies through cosmic time can go through different level of activities. And in particular, one of these episodes of activity is either the quasar mode, or we'll see a bit later about the radio mode. So the power comes from the very central region, and I'll show in a bit some great images that we got thanks to the Event Horizon collaboration a few years ago. The idea is that there is something that we can associate with a supermassive black hole. So a black hole that behaves like a black hole in the theory of general relativity. You have this supermassive black hole with masses of the order of 10 to the 6 up to 10 to the 10 solar masses. We might have the singularity at the center, but who knows? We'll focus more on the surroundings. And in particular, we think that the power from quasars and active galactic nuclei comes from the accretion of matter onto this black hole. So you can see the accretion disk around, and if you go farther away from the inner structure, you have this kind of donut structure that is typically called the dusty torus. You can have broad and narrow line region in the optical. Those are very useful, in particular the broad line region, to estimate the mass for these objects. And of course, you can have relativistic jets. This is kind of the standard picture that we had until a few years ago. Something that we need to include here, for instance, is the presence of outflows. Large-scale sub-relativistic outflows, and also more objects here in the center. And I will talk later about outflows and also potentially binary systems. So here is a spectacular image. I think people also from here contributed to this one. So you can see M87. M87 is a giant elliptical galaxy at the center of the Virgo cluster. And you can see images here in radio in increasing frequency, so in increasing angular resolution. And here you see this huge structure, of course, you know better than me, the radio jet on scales of tens of thousands of parsecs, so even outside of the host galaxy. If you zoom in, you start to see this structure here, which is a relativistic jet. We see the boosted and deboosted parts, the lobes. And if you zoom in, you start to go closer and closer to the very core, the very center of this galaxy. And in 2019, we saw the first image of something, I mean, some structures near, very close to the horizon of this object. So we know that at the center, there are supermassive black holes. I mean, not yet we know if they are exactly as expected in general relativity, but they behave at certain distances like those ones. Okay, so that was an amazing picture to show that supermassive black holes do exist. They are at the core of galaxies, and they can affect scales up to even megaparsec scales from the center. And this implies a release, an enormous release of energy. We also have other indications connecting supermassive black holes to their galaxies for active and non-active galaxies. Here you can see the famous M-sigma relation that says that the higher is the mass of the central object, the larger is the velocity dispersion of the stars. And this slope is very tight. Another indication of the need of some sort of feedback, of release of energy from the core of galaxies to larger scales comes also from comparison of populations of galaxies, and in particular the stellar mass of galaxies in the high end with numerical simulations. If you don't consider the effect of AGN feedback, you would overpredict the number of massive galaxies. Instead, we need a cutoff here, and this can be done by AGN feedback. However, we should remember that a supermassive black hole, yes, is huge, but is not that big compared to a galaxy. In particular, it's about the same comparison of a €1 coin with the whole planet Earth. That's the different sizes that we are dealing with. Also, the mass of a supermassive black hole is only about 0.1% of the mass in stars in the bulge of galaxies. So it's negligible from the point of view of mass and size. However, if you just simply calculate the gravitational energy in a black hole, because it is massive and so compact, this energy can be larger than the binding energy of an entire galaxy bulge. So if we are able, if nature is able to release a fraction of that energy into radiation and mechanical energy, that can have an impact on the host galaxy itself. In particular, we could even imagine a galaxy to explode itself. If we have some high Eddington accretion, for instance, and that's something that people start to see at very high redshift, where we see this huge extended nebula around very luminous quasars. So regarding mechanical feedback, there are two flavors. They come in two flavors. One is through relativistic jets. And of course, here, the name relativistic jet tells us that we have relativistic particles accelerated somehow thanks to the magnetic field. And here, disk winds, so outflows, winds, less collimated, produced by the accretion disk around the central black hole. And here, the acceleration mechanism is still unclear. It can be due to radiation. If you talk to some people that they don't deal with radiojet, they prefer radiation because they say that MHD is complicated. But if you talk to the radio community, of course they say no, MHD works because we see the radiojet. So it's most likely something in between, and both of them we'll see a bit later. They come from similar objects, a supermassive black hole with accretion, and you have magnetic fields, basically. Sorry. Here is just to show you one of the many, sorry, some delay. Okay, we're gonna make it. It's one of the many simulations of people that do to study the cosmological evolution of structures in the universe. And in particular, here you see a large-scale simulation of a volume of the universe and the formation of galaxies, the collapse of objects into galaxies. And here you can see the effect of assuming no feedback at all from the central supermassive black hole. And here is the case with the feedback from star formation and AGN. And you can definitely see that the situation here is different regarding the distribution of the gas, for instance, temperature. So structures are different if we consider the presence of black hole, the black hole, and of course, also stars. This is one of the possible sketch to think about galaxy evolution and connecting supermassive black hole activity and star formation. So here you can see from simulations, you can see that the luminosity of a quasar compared with the star formation rate, and it seems to be relatively well correlated. And there is a delay. The star formation is typically starts first. You have matter flowing in, stars are getting born. A fraction of that gas, 99.9% forms stars. 0.1% goes into the innermost regions and power quasars. But once you have the quasar that is active, you start to potentially quench star formation. And the quasar quenches both star formation and the activity on itself. So the feedback is both on star formation and black hole growth. And here is kind of a possible sequence. You see, you start with disk galaxies. You are in a group. Here, there is the assumption that mergers are very important. Of course, they can trigger the most luminous quasars. But for other sources, you don't need such major mergers. But let's follow here. So you start from a group. You start to have interactions. You can start to have mergers of galaxies. And here you can observe some particular type of galaxies, which are called Lyrt or Ulyrt. I'll show later about one results on one Ulyrt. Here you have the mergers of these two galaxies and the two supermassive black holes. So these are the objects from which we would expect also to have gravitational waves. Then you have the blowout phase when you are activating, when you are increasing the matter flow to the central region. You activate the quasar. There is the blowout phase where outflows, jets, and radiation is pushing away the gas. You have the quasar phase where you actually see the inner regions of these objects, and then this slowly decays into potentially a dead elliptical galaxy. This is just, I mean, a very quick, broad sketch of this possible phenomenon. But let's try to go and see if we can observe directly these outflows produced from the accretion disks. So back in 2007 until 2010, we started to work on these projects. And at that time, these features, these absorption features here were considered kind of people believes or not. Nowadays, of course, we have many more data, many more models, etc. So now we know that a significant fraction of AGN in the X-rays, they show outflows through blue-shifted absorption lines with velocities which are potentially very high, mildly relativistic, 10, 20, 30, and even 70% of the speed of light. Here are some studies that try to investigate what happens not on single objects, but on a population of sources. This one was a study that we did in the past on a local, low redshift, relatively low luminosity AGN. And at that time, we found the presence of these ultra-fast outflows in more than 40% of the cases, both type 1 and Compton-thin type 2. We saw variability on hours and days, indicating again that they are coming from the very innermost part of the accretion disks. The velocity distribution, you can see here, goes up to 30% of the speed of light. There could be limitations due to signal to noise, etc. So potentially they can go even higher. But already these velocities here are velocities which are approaching the jet. If you would observe a structure moving at this velocity here in radio, you would say it's a jet. It's a subrelativistic jet. But if you start from the other point of view, it's a high velocity or ultra fast outflow. These are highly ionized, mostly, but not only, high column densities. And here, back 10 years ago, we were finding consistent results between two different satellites. So these were not artifacts of one particular instrument. Many people here worked on other projects to expand in different directions these population studies. For instance, here there is a paper a few years ago by Chartas in which they studied outflows in 14 lensed and non-lensed quasars, so moving from local objects up to a redshift of 4, so going towards the peak of the AGN population. In this case, very interestingly, we have that about 90% of the objects, they show these very fast outflows. So in the past, these outflows were more common, perhaps because we are closer to the peak of the AGN activity. Also the velocities, here we can see velocities from 0.1 up to 0.7 speed of light. So we are approaching something that can be close to a relativistic jet. The launching radius with these velocities basically is very close to the black hole, about 10 gravitational radii. We are approaching the ISCO. So these are outflows produced near the ISCO of these massive, supermassive black holes, not yet relativistic jets, but we are getting closer to them. The power is also very high. On average, seems to be about 50% of the volumetric luminosity, which is important for AGN feedback, and its very high volumetric luminosity suggests that we cannot use only radiation to accelerate these outflows, but we need MHD. So potentially a similar mechanism that accelerates jets. In other sources, for instance, if the black hole has a lower spin, or if the accretion disk is in a configuration which is less, is not able to collimate a jet, you end up with producing very high velocity, uncollimated outflows. Here is a results from another study, the subways, that is led here in Bologna by Marcella. Here, basically, they moved to moderate redshift, moderate luminosity. So the population was moved to this other step, which is basically filling the gap between the high redshift universe and local objects. And there seems to be a continuity between the local population of AGN and these other sources here. They find the outflows to be present in more than 30% of the objects. Parameters are globally consistent with the local sources. And there are correlations, for instance, indicating the outflow velocity and luminosity. So the higher the luminosity, the higher is the velocity of these outflows. And also more massive, supermassive black holes have higher mass loss through these winds. So far, these studies were focused on radio quiet sources. So sources in which there is no clear evidence of a powerful jet in radio. We are working on a few years that thanks to the student Simone, we are finalizing a study comparing radio quiet to radio loud objects. So what happens to the wind in these two classes of objects? We know the dichotomy between radio quiet and radio loud objects, but we wanted to investigate if there was a similar dichotomy in winds. And surprisingly, there seems to be no dichotomy. So both objects, bright, radio quiet, and radio loud AGN, show very similar accretion parameters, so Eddington ratio and accretion rate. And also that these winds are very similar. Here you can see a comparison in the velocities. Also, we find that a comparable amount of material that is accreted on the disk is actually also ejected through outflows. A main difference between the winds and jets is that jets are typically thought to be lightweight, but very powerful in power, kinetic power. Winds are capable of transporting baryonic matter. So we see them through the presence of ions. So it looks like, and this evidence is found by ourselves, by the previous studies, that a comparable amount of matter goes into the black hole before going into the black hole is ejected in winds. So this tells us that there is some level of feedback, not only between the black hole and the host galaxy, but between the black hole and the accretion itself. As simulations also showed, accretion is not smooth, is not continuous, but it is more variable with a certain duty cycle. Also, it is found that the most energetic outflows are found in the most luminous AGN, something that we are starting to have, that this result is more and more robust. So more luminous objects, not necessarily more massive, but more luminous, it means with a higher accretion rate, they show more powerful outflows. But if we want to go, for instance, into one path here, the comparison of these winds, the accretion disk, and jets, there have been some interesting evidences in the past. For instance, in this particular case, this one is the radio galaxy 3C111. And in this long-term monitoring, you see this is about 6 years in the X-rays, and also monitoring in a high resolution VLBA radio images, people started to correlate the ejection of knots in the radio jet. So the radio jet in the innermost part, here is the core. The supermassive black hole should be within or near this central core. And over time, you see that there are blobs ejected. And if you can trace them over time, you can estimate their velocity. The interesting thing is that every time there was a new blob ejected in the jet, there was a dip in the X-rays. And that's something that people observed also in some X-ray binaries. So the accretion onto black holes of different masses is not the same, but at least there could be some similarities. In this particular object, we also had long observations with XMM Newton for spectroscopy, deep spectroscopy, and we found that during the dips, also the outflows, the ultrafast outflows were stronger. Of course, we only had two. It's very expensive to do this type of monitoring, but these two detections of the outflow were within these dips and were correlated in time with the ejection of these knots in the jet. So there are some disturbances in the jet propagating through the jet that are also correlated with some disturbances in the inner accretion disk and in the production of winds. But going to the larger scales, probably we need to move a bit faster. We need to know the power. We need to know how much power we can have in these outflows to inject in the host galaxy. I mean, and that's difficult because we need several parameters, none of which, only one of which is well estimated from observations, the outflow velocity, but we need the covering fraction of the outflow, the density, and the launching radius. So far, it looks like that the ultrafast outflows are good enough for AGN feedback, but the uncertainties are huge. So in order to overcome this, we started to develop a new code called wine. You can see here, probably we drank too much wine, especially Alfredo during his PhD. But now the code is available also for the public. You can download here. We have some templates. Just quickly going through these is a self-consistent model for emission and absorption from an accretion disk wind that incorporates also density and velocity profiles, and you can also change the geometry of the wind. And you can directly use it to fit data. Here, just to show that the absorption is modeled through a series of shells, and for each shell, we calculated the photoionization. Instead, the emission is calculated through a Monte Carlo code that again uses photoionization to have the emission lines from different ions. If you put them all together, then you have absorption and emission from the wind, so something that is called the P-Cygni profile. And that's important to estimate the main parameters, as we have done in this case. This is the quasar PG1448. Here is the possible P-Cygni profile in the X-ray data. And here is the fit with wine that we did a few years ago. And in this case, you can see that the fit is very good. Only through emission and absorption from the accretion disk wind, and we find a launching radius of about 77, of course, about 70 Schwarzschild radii, high column. The average velocity is 15% of the speed of light, large covering fraction, more than 70% of the sky is covered by the outflow. And from this, we estimated better the mass outflow rate, which we find to be twice the accretion rate. And the volumetric luminosity, the power of the wind, which is about 24% of the volumetric luminosity. So we're getting something even more powerful of what people required from numerical simulations. But of course, these are instantaneous quantities. If you integrate them over time, sometimes you have the wind, sometimes not. On average, it can be of the order of a few percent. Something interesting that I think in the radio community these are like normal things, is to have special relativistic corrections when you have matter moving at relativistic speeds. But that's something that in the wind community was never done, because typically they were moving much slower velocities. But we did this with Alfredo and another very, very good bachelor student, which now moved to economy, a PhD in economics. Anyways, but he published this paper while he was doing the bachelor. So here you can see an effect, which is the deboosting. So simply speaking, is that if you have your source of radiation and you are on top of your on the outflow, you see the source of radiation moving away from you. So it is redshifted, and basically the luminosity that you get is deboosted. That poses also a limit on radiation pressure. Now you can accelerate these outflows, and also on the strength of the observed opacity. Because you have a lower luminosity that encounters the outflow, you are underestimating the column density and the opacity of the wind. So faster outflows, they become also weaker and weaker in features. So perhaps we are not observing them, or it's so difficult to observe the most powerful, fastest component of these outflows, just because for special relativistic effects, their features become weaker and weaker in the spectrum until they completely disappear when they go close to the speed of light. Another effect is the Poynting-Robertson effect applied to outflows. If you have a plasma which is outflowing, this plasma is recombining, is emitting photons through emission lines, but because it's moving at relativistic speeds, these photons are emitted preferentially towards the direction of motion. And basically, it's like a recoil. It's like you shoot a photon, most of the photons on the direction of motion, and you are slowing down the outflow. So the faster the outflow, the more this effect of drag is important. So basically, this poses important limits on the velocity that you can reach with the radiation driving. So I think it keeps still open the door for MHD driving. Then how can you connect small scales to larger scales? But that's very, very tricky. Many people also here started to do several years ago. This is just an example. The first case in which we found a connection between a large scale cold outflow and an inner hot outflow from the accretion disk. Here is this galaxy here, which was called also Attila. So IRAS F11119. Here is the P Cygni profile in OH, so in infrared. You can see an outflow in molecular gas with a velocity of up to 1,000 kilometers per second, a very large mass flux, and so on. This was later confirmed with ALMA through the CO emission line, through the broad wings, up to 1,000 kilometers per second, and recently also with O3 observations led by Tombesi et al. The paper is almost published, right? And also here in this ionized gas, there is evidence for outflows at thousands of kilometers per second in the host galaxy. And this galaxy is a Ullrich. So it's a post-merger Ullrich. What happens in the very core of this galaxy? We explored it back a few years ago with Suzaku, and we saw this huge absorption trough. You can see the signal to noise here is not huge. Of course, when you have absorption, the stronger the absorption, the less photons you get, and therefore the less signal to noise you get. But here there was an indication that more than 5 sigma of an outflow with a velocity of 25% the speed of light coming from the core. This was then confirmed also by NuSTAR. So an independent satellite observed the source a few years later and again observed an outflow, a persistent outflow from the accretion disk with a comparable velocity. And more recently, also with XMM Newton, in the paper by Lanzuisi, by Giorgio et al., to be published very soon. This was again confirmed almost 10 years after, roughly, almost 10 years after, with XMM Newton, and this time also there are more components that have been found. Not only the iron K band, but also an outflow with a lower ionization, but with a similar velocity. So we are starting to enter, the more you look at these objects, the more data you get, the more complex, multi-phase, and multi-scale these objects appear to be. This is just a video, but probably here we could be too slow, just to show the possible connection. 10 minutes, okay. So here is just to show you that we are pushing on these studies. This is an example with James Webb. We have a proposal approved in order to look into the details of the molecular outflows, in particular in a sample, in a very good sample of fluids, of course, where these outflows are more clearly detected, more powerful. And very recently, we got also the launch of another X-ray satellite. So recently we got XP for X-ray polarimetry, which is doing spectacularly. We got, I mean, the results which were totally unexpected. XP is more focused for galactic objects. There are observations of extragalactic objects as well, but the signal to noise is not too high. In this case, if we want to study winds, we need to go into spectroscopy because we need to observe absorption lines. And in particular, the launch of XRISM in September 2023 will be transformative. If you don't, I don't tell you the story, but basically, this is something that some people have been working on this technology, the microcalorimeter, since the 1980s. And finally, we start to see results. The cycle 1 proposals was concluded in April. Now we are performing the PV phase observations, performance verification observations, and I'm actually part of a team that will observe the quasar PDS456. I'll talk to you about this a bit later. But here you can see what it is public now. This is the first very high hyper-resolution iron K spectrum of an AGM. This is NGC 4151, is the X-ray brightest local AGM. And if you would see the data, the quality of the data before, basically these were just a few data points. Now we see everything is very sharp, very sharp features, unexpected features. Something that we started to see, this is just a simulation. I cannot show you the data of PDS456 yet, because we got them just a few weeks ago. It was observed in between March and April. We were a bit skeptical because the satellite is working fine, the instrument is working perfectly, but there is an issue with a filter, which maybe later is gonna be opened. So we have a lower signal to noise. We needed to increase the exposure time. We thought, okay, maybe that's not good enough. The source maybe is not behaving, but actually it's something that really spectacular. And what we start to see is that we start to see forests of lines everywhere. Something that before was one feature, now is many, 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 many features. So we start to see the complexities, the fine structures, in particular of these outflows. And then the problem is reverse engineering the multi-phase and multi-scale structures of these objects. But stay tuned, in a few months, I think we will show something. Move quickly here just to say that there are a lot of work studying, trying to connect the small scale outflows to the larger scales, and potentially we can do that through models of momentum driving and energy driving. So all these models imply a shock propagating in the host galaxy that then either conserves only momentum or conserves energy. Going fast here, you see also a lot of correlations that we start to see from a different type of objects and different type of winds, from molecular, ionized, broad absorption line quasars, and X-ray outflows. I want to move fast to show you something at the very end. The other interesting thing is that if these winds, now we see them, And if they are so fast, when they produce shocks with the environment, they can produce very powerful shocks. And through these shocks, you can have also particle acceleration. And you can have, for instance, cosmic ray acceleration through these wind shocks. You can have a production contribution to the gamma ray background, and even neutrino, because these are the outflows are transporting matter, hadrons. So basically, you can also have some level of neutrino fluxes. We are finding evidence for a possible gamma ray emission from a non-jetted AGN. There's been a lot of work on this object because we need to distinguish in the sky where the object is and so on. But potentially we could start to see gamma rays from these shocks. So basically, if you remember the Fermi bubbles, if the Fermi bubbles are interpreted as due to the past activity of Sagittarius A star, basically we would expect to see similar bubbles as background emission in other objects. The more powerful, the more massive is your supermassive black hole, the more powerful these bubbles should be. So I'm at the very end, and here I would like to show you something that has been the work of the past 3 years. I mean, I didn't work on this, but it has been kind of, let's say, we need to spend time on this, and it was rather difficult because basically we started a few years ago. In late 2020, there was an evidence of a transient source. And this transient, observed by the Assassin collaboration and then many others, Assassin 20QC, then was followed up with X-rays, optical, and so on. And initially, people thought, okay, this could be just, you see, here there is nothing, there's a quiescent galaxy, then you start to see this transient in the nucleus of this galaxy, and it could be a tidal disruption event. It was followed up, and in particular here you see the light curve during this peak activity with NICER, which is an X-ray telescope on the space station, and we started to notice these kind of little dips here. It's okay, that's weird. And also, it didn't behave exactly as expected from a tidal disruption event. Here you can see the optical with Gaia. So initially it was an optical transient, and then there was X-ray emission. The X-ray spectrum, for me, that basically I mostly studied bright AGN. I'm more used to power laws. This is basically just a black body, pure black body. It's a black body with a temperature of about 100 electron volts. So potentially is a tiny disk, similar to what people see in tidal disruption events. So potentially this event initially there was a supermassive black hole there with a mass of about 10 to the 7 solar masses. It was in a very, very low level of activity. So either very low luminosity AGN or even quiescent. Then potentially a star came too close to this black hole. There was a tidal disruption event. We started to see the rising of the optical light curve, then the X-ray light curve. And once you start to have a lot of luminosity, that was amazing. We started to see the broadline region appearing. So basically, all the classical structures that we thought would be present in an AGN were still dynamically there. There was the broadline region orbiting, and we started to see it because there was light coming from the center. Then we started to see also emission line from the nanoline region. So there was no torus. So basically, it was like almost an empty supermassive black hole that didn't have much matter around. But thanks to that star that provided about half of its mass for the black hole, for the accretion disk, we saw this emission. And when we started to model this, we saw that during these dips, there was an evidence for this decrease of flux, potentially absorption. So then we started to calculate a simple deficit ratio. So a ratio in the band where we would expect to see absorption with respect to the band where we expect to see the continuum. So the lower this ratio, the stronger is the absorption. And while observing this object over time, we saw that there were these recurrent dips in this ratio. So basically, this was indicating that the absorption was varying on quasi-periodic timescales. These timescales are of the order of 8.3 days. So I've never seen something like that. So we started to say, well, this is wrong, or it's something, because seeing absorption varying on 8.3 days is something. If you imagine a galaxy, something varies on this short time scale. So we started to model the data. We started to use also more complex timing analysis and so on. And here you can see that the frequency of 8.5 days is very significant, more about almost 5 sigma. And fitting the data during these intervals, we saw that there was a continuous presence of an outflow, but during these dips, the outflow column density was increasing, was becoming stronger, from 10 to the 1 to 10 to the 22 centimeters to the -2, and the outflow has a velocity of 30% of the speed of light, observed through oxygen 8 emission absorption lines. So we started to say, okay, we excluded many other possibilities, disk instabilities and so on, because time scales were not correct, and you would not expect to see this level of coherence. So basically, we think that we are seeing a new phenomenon called quasi-periodic outflows, QPOuts, that are caused by a wind launched from the accretion disk at a distance of about a few tenths of gravitational radii from the black hole. Then in parallel, we thought, okay, this is maybe too speculative. But in parallel, there was a group in the Czech Republic that was actually doing simulations of objects embedded, so within accretion disks of AGN. And in particular, they were observing that when you have an object going through with a certain orbit through the accretion disk, it will either increase the luminosity of the disk or it will increase the absorption if you have outflows. And in their simulations here, they used the, you can see here the accretion disk basically is an adiabatic simulation with a MED assumption. And basically here, the outflows are generated through magnetic forces. Here in the inside, you would expect to be the jet. There is no radiation here. So the simulation by itself, this was then done with our own parameters in order to be more similar to what we would expect to see. Basically, from the simulations, you see here the mass accretion rate, but here you see the mass outflow rate. The mass outflow rate on the upper and lower part of the disk shows a QPO. It shows a variability which is recurrent on timescales of about 8.5, 8.3 days, if you correct for the redshift. And that's the timescale of the orbit of the secondary object through the accretion disk of the main supermassive black hole. Every time the object goes through, in particular, if you're observing through here, the outflows are boosted every time. So here we think that there is a perturber with a mass in the range 10 to the 100 to 100,000 solar masses. So basically the perturber, which is perturbing the accretion disk, the small accretion disk of the main supermassive black hole, is at a distance of about 100 gravitational radii. So these results, together with others, for instance, the QPE, yeah, I'm done, are basically suggesting that we don't have the standard picture of an AGN where you have supermassive black hole, the accretion disk, but this region can be crowded by many more objects. This is something that I remember when I was studying here initially, AGNs, there was the initial hypothesis of a star cluster in order to explain the nuclear activity of galaxies. Well, and also we see a lot of objects around Sagittarius A star. So basically, these type of objects, which are recurrent nuclear transients, can be the electromagnetic counterpart or even precursors of extreme or intermediate mass ratio in spirals that eventually could be observed through gravitational waves, because the closer, I mean, if you have an accretion disk, the system will start to lose energy, and this is the way in which you can have the supermassive black hole to merge together with the smaller objects. And eventually they will produce a signal observable with LISA. I'm done. Sorry if it was a bit too long. Thank you.